How many of you have ever looked up at the night sky and wondered, are we alone? It's an age-old question, but a man named Enrico Fermi once thought about the same question. He pointed out that with billions of stars in our galaxy alone, and many with planets in the habitable zones, we should have seen some sign of extraterrestrial life by now. This is the essence of the Fermi Paradox, which says, where is everyone? It's just like throwing a massive party, but no one shows up. Not even a text. So are we looking in the wrong places, or is intelligent life really that rare? Let's get into the details of Fermi Paradox and some fascinating theories that attempt to undo this cosmic mystery. It all started in 1950 when a group of scientists at Los Alamos were talking about UFOs and super-fast space travel, and Enrico Fermi asked a big question. Where is everyone? The room fell silent because, well, nobody had an answer. Originally, the question was meant to attack the idea of interstellar travel, the possibility of which Fermi wasn't confident in. He wondered why, with so many stars in the sky and a good chance of other smart aliens out there, none have visited us yet. This question is the Fermi Paradox. To understand why Fermi was puzzled, think about how old Earth is. It's been around for about 4.5 billion years. Our galaxy, the Milky Way, is huge, about 100,000 light years across. Even if aliens traveled at just a tiny bit of the speed of light, they could explore the whole galaxy in about 10 million years. That's a lot of time for them to visit us many times. There are around 100 billion stars in the Milky Way, and maybe 10% of them have planets where life could exist. So the chance of another smart life is pretty high, but it's strange that we haven't seen any signs of them. Fermi had a few ideas to explain this mystery. He thought maybe traveling between stars is impossible, or maybe aliens think it's not worth the effort. Another idea is that smart civilizations don't last long enough to travel between stars. Some other ideas say aliens might not want to travel everywhere in the galaxy, or they might like to live near stars that live a long time, skipping stars like ours. Since Enrico first asked the question about aliens, we've been looking for answers, mostly through the Search for Extraterrestrial Intelligence program, but we still haven't found anything. One idea is that advanced civilizations might not want to spread out all over the galaxy. They might prefer to live near stars that last a long time, not like our sun. This could mean that while there could be lots of life in the galaxy, these aliens might just not be interested in letting us know they're there. Fermi also thought about how many intelligent civilizations might be out there, which led to the Drake equation. This equation tries to guess how many smart civilizations are in our galaxy. It looks at things like how many stars are born, how many planets there are, and the chances of life evolving into smart creatures that can talk across space. So, according to Drake's equation, there are possible reasons for this great silence: the absence of communication from or evidence of extraterrestrial intelligence. One explanation could be that the development of life on Earth, which occurred relatively soon after the planet formed, is actually quite rare. This would mean that the likelihood of a planet developing is much lower. It's also possible that most of the universe might already be colonized and communicating, but we're in a remote area far from any activity. Scientists use the Kardashev scale to classify civilizations based on their energy usage. A Type 1 civilization can use all the energy available on its home planet, which we are approaching. Currently, most scientists believe we are at about 0.7 on the Kardashev scale, with a full Type 1 status estimated to be about a century away. A Type 2 civilization could harness the energy of its host star, while a Type 3 civilization would have access to the energy of its entire galaxy. So, the possibility is that highly advanced Type 3 civilizations may simply not see the value in communicating with less advanced beings like us. If they have the power of an entire galaxy at their disposal, they might not consider us worth their attention, especially if they can't relate to us using handheld cell phones. Some scientists have even suggested that the silence could be due to the existence of a predatory species that intelligent civilizations fear. In this scenario, civilizations would avoid transmitting signals to prevent revealing their location to these predators. Despite these theories, the general consensus is that if there are other civilizations transmitting signals, we might be listening incorrectly. Our current technology and understanding of the universe may not be advanced enough to receive or interpret these messages. The Homo genus, which includes humans, has been around for about 3 million years. If we compare this time to the age of the Earth, it suggests that the evolution of intelligent life is quite rare, with a probability of about 1 in 1,000. Our early ancestor, Homo habilis, first made tools roughly 2.6 million years ago. In contrast, radio technology, which could be used for interstellar communication, has only been around for a little over a century. By comparing these timelines, we can estimate that the fraction of intelligent civilizations capable of interstellar communication is roughly 1 in 26,000. If every suitable planet in our galaxy gives rise to intelligent civilizations, there could be many civilizations out there. However, if the chances of this happening are low, then we might be the only intelligent beings in the galaxy. According to the Drake equation, if a civilization could survive for at least a century after developing transmission technology, there could be around 10 civilizations in our galaxy. But what if civilizations tend to self-destruct shortly after developing this technology? If, for example, they typically only survive for about 10 years after reaching this technological milestone, then the number of civilizations in our galaxy could just be 1, us. This idea is summarized by American economist Robin Hanson as the Great Filter. It suggests that at some point between the formation of a habitable planet and the colonization of the galaxy, there might be a step in life's evolution that hardly ever happens. This could explain why we haven't heard from anyone else, because they might have hit a wall that stopped them from existing or talking to others. There are 2 main ideas about where this great filter might be. If it's behind us, it means that the difficult step in evolution has already happened, and we have somehow managed to overcome it. This would suggest that intelligent life like us is very rare, and that's why we haven't heard from anyone else. On the other hand, if the Great Filter is ahead of us, it means that there is a challenge or problem that advanced civilizations cannot overcome, causing them to disappear. This would imply that our future is also uncertain, and we might face the same fate as these civilizations. The Fermi Paradox has also given rise to some fascinating and unsettling speculative theories about the nature of our universe and our place within it. The first one is zoo hypothesis. This suggests that advanced extraterrestrial civilizations are aware of us, but are intentionally avoiding contact. They might be observing us from afar, like animals in a zoo, to allow for our natural evolution and development without interference. Connected to this is the simulation hypothesis, which proposes that our reality is actually a highly advanced simulation, possibly created by a more advanced civilization. In this scenario, the lack of contact with other civilizations could be explained by the fact that they simply do not exist within the simulation. This theory challenges our fundamental perceptions of reality and raises profound questions about the nature of existence and the fabric of the universe. Adding another layer to the mystery is the concept of non-biological intelligence. This theory suggests that extraterrestrial civilizations may have evolved beyond biological forms into non-biological entities, such as advanced artificial intelligence. These entities could exist in forms we cannot perceive or understand, using communication methods or technologies that are beyond our current capabilities to detect. Some people have criticized SETI projects, which search for extraterrestrial intelligence, using the Fermi Paradox as a reason. They argue that since we likely are alone in the universe, SETI projects are a waste of time and money. However, astronomers working in the SETI field respond that only a small amount of SETI has actually been done. Jill Tarter, an American astronomer, and her colleagues have compared the task of finding extraterrestrial intelligence within the vastness of space to trying to determine if fish exist by scooping a glass of water from the ocean. In other words, the scale of the universe is so immense that we have only just begun to scratch the surface in our search for intelligent civilizations. The universe's edge is a fascinating concept that challenges our understanding of space and time. You might wonder what is beyond the edge of the universe, or it's just infinite. Let's break this down in a simple way. We talk about the observable universe, which is the part we can see and measure. It's 93 billion light years across with a radius of 46 billion light years. This edge is actually the limit of what we can observe, not a physical boundary. Beyond this, there might be more universe that we can't see or interact with. General relativity suggests the universe is flat and could go on forever. However, measuring the universe's curvature precisely is incredibly challenging. The flatness doesn't mean a two-dimensional surface, but rather that the rules of geometry we understand, like parallel lines never meeting, apply on a cosmic scale. Some argue that since we can't interact with or observe what's beyond the observable universe, it's not a scientific question. However, science often explores the unknown, even if we can't directly measure it. The observable universe's edge is tied to the particle horizon, the furthest distance from which light has traveled to us since the universe began. This horizon defines the known universe's boundary. But reaching the particle horizon is not straightforward. The universe is expanding, meaning the further we try to go, the more space stretches. To visualize this, imagine traveling towards a distant point while the ground beneath you stretches out, making the journey increasingly longer. Even if you traveled at the speed of light, you'd never actually reach the particle horizon because space continues to expand. This expansion leads to the concept of an event horizon in the universe, similar to the event horizon of a black hole. Beyond this point, even light can't reach us because space is expanding too quickly. Thus, the universe's edge is not a solid boundary, but a limit of what we can either observe or interact with. In simpler terms, while we have a measurable edge to our observable universe, the true extent of the entire universe might be far beyond our current understanding or reach. The expansion of space means that parts of the universe are forever out of our grasp, creating an infinite journey towards an ever-receding horizon. This infinite nature makes the universe both an endless source of curiosity and a profound mystery. Just imagine the universe as a vast, ever-expanding bubble. Within this bubble, there's a boundary called the event horizon. Beyond this event horizon, nothing, not even light, can ever reach us. This is because the space beyond this point is expanding so rapidly that even light, the fastest thing in the universe, cannot bridge the gap to get to us. Currently, our best measurements suggest that the event horizon is about 16 billion light years away from us. This means there are galaxies we can see now, but they are so far away that any new signals they emit will never reach us. It's like watching the light from a distant ship that's already sailed beyond the horizon, where we'll never be able to contact it again. There's another boundary called the particle horizon, which is the edge of the observable universe. This is the farthest distance from which light has had time to reach us since the beginning of the universe. Interestingly, the particle horizon is farther away than the event horizon, so there are regions of the universe we can now see thanks to the light that left those places long ago, but can never actually reach or send signals to because those regions will move away faster than the speed of light due to the universe's expansion. As the universe continues to expand, more and more of it will cross the event horizon, moving out of our reach forever. This means that over time, we'll lose the ability to observe or interact with many parts of the universe we can see today. It's a bit melancholic, knowing that as time goes on, we'll be able to see less and less of the universe. But what if we could break this cosmic speed limit, like the theoretical Alcubierre drive, which bends space-time to allow faster-than-light travel? We could potentially reach beyond the event horizon. Let's imagine we have such a spaceship, and we use the energy of entire stars to power it, chasing after the particle horizon. What would we find? Even if we could instantly travel to the particle horizon, we would simply see more of the universe. This is because the particle horizon is not an absolute boundary, but rather the edge of what we can currently observe. If you move to the edge of the observable universe, your new vantage point would have its own observable universe around it. The Milky Way would appear as a small part of the cosmic microwave background, the leftover glow from the Big Bang, in this new observable bubble. You would see a similar distribution of galaxies and clusters all around you, just as you do now. So, even with a warp drive, you wouldn't find anything fundamentally different. The universe would still appear vast and filled with galaxies, just from a new perspective. It shows that no matter where we go, the universe remains a large, intricate expanse, always offering more to explore, but with the same similar patterns. Beyond the edge of the observable universe lies a realm that depends on the geometry of the entire universe. On a small scale, the universe appears bumpy because of stars and galaxies, but on a large scale, it's quite smooth, like gentle waves on an ocean. Observations of galaxies in the cosmic microwave background, CMB, indicate that space-time is very flat. If space-time is perfectly flat, applying Einstein's equations simply suggests that the universe is infinite. If the universe is infinite and we somehow cross the particle horizon, the universe would continue endlessly. This concept of infinity is fascinating and complex, with some types suggesting infinitely repeating versions of our own universe. However, it's uncertain if our universe is perfectly flat. Consider the Earth. It looks flat locally, but from space, its curvature is evident. The universe might also have curvature that's too subtle to detect with our current measurements. If this curvature exists and is positive, the universe might be like the surface of a hypersphere, the 3D surface of a 4D sphere. In this scenario, traveling in a straight line through the universe could eventually bring you back to your starting point. Recent estimates suggest that if the universe is curved, the minimum radius of this curvature would mean traveling at least 18 times the distance of the particle horizon to complete a loop, assuming the universe's expansion halted during the journey. However, this idea relies on straightforward applications of Einstein's equations. While general relativity is powerful, it's not the ultimate theory of everything. There are intriguing ideas about cosmic inflation, suggesting our universe could be a slowly expanding bubble in a vast, exponentially expanding multiverse. These bubble universes might be finite in size regardless of their internal geometry, possibly having a true edge. What lies beyond such an edge is unknown. The laws of physics or even the numbers of dimensions might differ. Addressing whether it's contradictory to use Einstein's theory to validate itself, testing a theory indeed involves using it. Yet, relying on a single prediction isn't enough. Multiple consistent predictions strengthen the theory's validity. For a scientific model to be accepted as a theory, it needs to make multiple accurate predictions. General relativity is one such theory with many successful predictions. For instance, GR can predict the orbits of planets around the Sun. By studying these orbits, we can calculate the Sun's mass. Then, using this mass, we can predict how much light will bend when it passes close to the Sun, a phenomenon known as gravitational lensing. The predictions made by GR match the observed deflection of light perfectly. This same principle applies to galaxy clusters. By observing the orbits of galaxies within a cluster, we can estimate the mass of the dark matter present in the cluster. The gravitational lensing caused by the cluster should match this mass, and indeed, it does. Someone asked why stars and planets aren't filled with dark matter. This is an interesting question. Dark matter is described as cold and clumpy, meaning it gathers to form galaxies. However, it doesn't interact with itself except through gravity. This lack of interaction means dark matter can only clump together to a certain extent. For dark matter to collapse into a star-sized object, it would need to lose a significant amount of energy. Losing this energy is difficult without electromagnetic interactions, which dark matter doesn't have. In contrast, the hydrogen gas that makes up much of our galaxy can clump together into large clouds. These clouds can radiate light, allowing them to cool further and collapse into stars. Dark matter cannot radiate light, so it remains more spread out or puffed up compared to regular matter. General relativity remains one of the most successful theories because it can make precise predictions about various phenomena, from the orbits of planets to the bending of light around massive objects. Dark matter, while still a mystery in many ways, follows different rules than regular matter, explaining why it doesn't form stars or planets. So, what do you think lies beyond the observable universe? Let us know in the comments below, and if you'd like to see more content like this, don't forget to like and subscribe.
We should be hopeful that this is a simulation, because otherwise...
Do you know that in 1970, British mathematician John Conway created the game of life? Despite its name, it's not a game you play in the traditional sense. Instead, it's a zero-player game where you set initial conditions and watch the simulation unfold according to a few simple rules. Once you set it in motion, the game runs on its own. Some patterns die out quickly, while others continue indefinitely. This idea sparked a thought. If such a simple simulation can produce complex behavior, what if we scaled it up to the size of a universe? A simulation that includes galaxies, planets, and life. More intriguingly, if such a simulation were possible, how could we know we're not already living in one? Initially, the idea that our universe could be a simulation sounds far-fetched, but when you delve deeper, it becomes more plausible. We perceive the world through our senses, creating our own subjective reality. This personal experience is based on our sensory inputs and brain activity. However, proving the existence of an objective reality, one that exists independently of our observations, is challenging. Objective reality would be a reality that exists regardless of whether we observe it or not, but proving something exists without observing it is contradictory. Consider this. Can you prove anything outside your own mind is real? This question touches on the nature of reality and consciousness. Babies provide insight into this as they develop object permanence, the understanding that objects continue to exist even when not perceived. Before about 1.5 to 2 years of age, babies don't grasp this concept. Playing peekaboo with a baby, for instance, reveals that they believe you disappear when you cover your face, only to reappear when you uncover it. This developmental milestone shows that the belief in a continuous objective reality is learned over time. However, even as adults, our belief in object permanence is part of our subjective reality. We assume things exist when we're not observing them. But can we be certain? It's our consciousness that allows us to observe and interact with the world. For example, we know that all matter is made up of atoms, but we can't see them without a microscope. This means that atoms, and by extension, the reality we accept, are only observable when we have the means to perceive them closely. This observation can simplify the concept of simulating a universe. Simulating billions of galaxies over billions of light years would require immense computing power. However, a more efficient approach might be to simulate only the conscious experiences of the beings within the universe. If everything we perceive is part of our subjective reality, a simulation wouldn't need to render the entire universe in detail all the time. It would only need to simulate the parts that are being observed by a conscious mind at any given moment. This raises an intriguing question. Could the people we interact with daily be complex functions within a simulation? If our consciousness and perceptions can be simulated, how do we distinguish between real beings and simulated ones? The idea that our universe might be a simulation is an intriguing and mind-bending concept. It's based on the notion that just as video games only render what the player sees to save computing power, our universe might do the same. This means that if no one is observing a particular part of the universe, it might not actually exist until it's observed. This is similar to the philosophical question, if a tree falls in a forest and no one is around to hear it, does it make a sound? In a simulated universe, if no one is there to witness the tree falling, it might not make a sound, or even fall at all, until someone observes the scene later. One argument supporting this idea is related to the progress of technology. Over the past 100 years, technology has advanced significantly. If this trend continues, it's conceivable that we could develop computers with nearly unlimited power. This would allow us to create highly realistic simulations, but generating these simulations would require an immense amount of energy. This is where the concept of Matryoshka brain comes in. Imagine the Russian nesting dolls, but on a cosmic scale. If an advanced civilization could build enormous structures around a star to capture its energy, it could harness enough power to run countless simulations of entire universes. These structures would layer around the star, capturing all its energy output. If this civilization replicated this process with multiple stars, they could potentially simulate many universes simultaneously. Currently, we already have projects like the Illustris project, which simulates the universe on a large scale using current computational power. As technology improves, these simulations will become increasingly accurate, possibly to the point of being indistinguishable from reality. However, even the best simulations will always have limitations. For instance, the Heisenberg uncertainty principle in quantum mechanics tells us that we can never know both the position and momentum of a particle with perfect accuracy. This suggests that any simulation would have inherent imperfections, unable to perfectly replicate reality. To manage these limitations, a simulated universe might use various tricks to conserve resources. For example, if you try to run a complex video game on an old computer while doing many other tasks, the performance drops because the computer can't handle all the demands. Similarly, in a simulated universe, high-energy areas like black holes might be designed to slow down time to reduce computational load. This could even explain why the speed of light is a constant. It might represent the maximum speed at which the simulation can process information. Thinking about our universe as a simulation can also shed light on questions like the Fermi Paradox, which asks why we haven't found signs of other intelligent life despite the vastness of space. If we are a simulation, maybe other civilizations aren't simulated at all, or we simply haven't encountered them due to the constraints of the simulation. Our awareness of the universe might be as limited as deep-sea creatures' awareness of the world above the ocean. Just as these creatures have no concept of the land, sky, or outer space, our understanding might be confined to what our simulation allows us to perceive. This could mean that our observable universe is just a tiny part of a much larger reality. Or it could be all there is within the simulation. Perhaps the universe cannot exist without conscious minds to observe it. This idea suggests that the universe needs observers, like us, to be real. Another intriguing concept is that of simulated universes, which could explain the multiverse theory, the idea that there are multiple or even infinite universes. Near-death experiences, NDEs, add another layer to this discussion. Many people who have had NDEs report that their life flashed before their eyes. Researchers from Hadassah University in Jerusalem analyzed numerous NDE cases and found that most people lost all sense of time during these experiences. One person said, "There is not a linear progression. There is a lack of time limits. It was like being there for centuries. It happened all at once." Others mentioned experiencing different events simultaneously, even though their human mind later separated them into distinct occurrences. Another individual described being able to feel the pain of every person they knew, understanding their struggles as if living another life. These experiences make it seem like people step into an alternate reality where time doesn't exist in the usual way. This state allows them to analyze life in a way that living people typically cannot. This phenomenon might be connected to the feeling of déjà vu, where you feel like you've had the same conversation or experience before. Maybe, in another universe or simulation, you actually did. The concept of free will comes into question here. What if every decision we've ever made is pre-programmed into a simulation? Each choice could branch off into a parallel universe or simulation, leading us to this exact moment. Current technology, like the advanced robots and machines used by companies like Tesla, surpasses human performance and speed. Biological neurons in our brains operate at about 200 hertz, while modern microprocessors work at around 2 gigahertz. That's much faster. A superintelligent AI running on faster hardware than the human brain could think of every possible outcome and choose the best one. However, we are not superintelligent AI. Our brains have limitations in what we can observe and understand. Despite these limitations, we've made significant discoveries, especially in math. Math seems universal, with numbers and patterns appearing in everything from atoms to galaxies. These discoveries allow us to ask profound questions, like whether we are living in a simulation. If we were to put billions of possible simulations into a hat and pick one, what are the chances we would select the original universe, the one that created all the simulations? Perhaps an advanced alien species found traces of our DNA on a dead Earth and created a simulation to learn about our history. If that's the case, then hello, alien observers. We may never know for sure. All we can do is observe and hope that our game of life is one that we can win. What do you think? Could we be living in a simulation? Let us know in the comments below. See you on the next video. Bye.